Alright, so let's go ahead and look at the golden rectangle extra credit problem on page 1. Yeah, that works. Guys, started.
That's what we're doing. That's that question.
So golden rectangle is the extra credit problem. We're going to go over it. We're going to have problems that are similar to this problem that you guys need to know how to solve. Will be on a test, solving word problems that involve quadratics. So a golden rectangle is where we have, say, some rectangle, and you cut out a square, and you're presented with another golden rectangle. So then you can keep this pattern going on where, say, you cut out another square, and you have another golden rectangle, and you keep going on forever and ever and ever. Very good. Let's go back to. So here would be another golden rectangle. Here would be another one. And this whole thing would be a golden rectangle. This whole rectangle. So it talks about how these are in various paintings that I guess people that study art, they notice these shapes, these golden rectangles. So the extra credit assignment, congratulations to the one person who did it, was discussing the golden ratio, and I wanted to know what was the exact value for the ratio of the length of a golden rectangle to its width. So let's go ahead and let's continue this on another page and see how we go about figuring this out. Okay. So what we want to know is the ratio of, say, this length here to this width here. So we want to know, the golden ratio, which we write as this. We know that is going to be whatever that is. We know it's approximately, according to the text, 1.6, but I want you to find the exact value, which by doing so, you'll determine how they determine this approximately like 1.6. Okay, so we know that, that isn't the best looking golden rectangle because that looks like a square, but in the textbook there's a better image where this here is a square. So if we know we keep creating these golden rectangles every time we cut out a square, so what can we say? Couldn't we say then that this length here and this width should be the same ratio as this length here to this width? So let's express that. So we have L over W should be the same value proportionate to this length to its width. Again, on page 151, you have a better image than the one I have drawn here. So how could we express this length here? If this is W and this is L and this is W, I know why it's confusing. Let me just get rid of, I showed the pattern before. Let me get rid of this here. I was showing the pattern, in fact, with that rectangle and kept moving forward, so let's make it easier. Okay, it's going to make it much easier to understand. This was layer 1. I was showing you before, I was demonstrating that you can keep going, you can keep getting golden rectangles, and that you go on forever. Okay, so this makes it much more clear. So this is to this should be the same proportion as what? Is there a way we can express the length of this and the width of this using L and W?
I did
L sub 2 and W sub 2? Okay. Okay, you could do that. But how could we ever end up solving for finding the ratio of L to W? So let's think about this. What is the length of this new golden rectangle? What is this distance here? Exactly. So the length of this new golden rectangle is the width of the original golden rectangle. Okay. Hold on. Let's get a statement first. So let's not jump ahead of ourselves. We first have to take some idea and put it on, make an equation or statement that's true. Okay. What would now the width of this golden rectangle be? So this is a square where this is W, therefore this here must be W, this distance here must be W, and this distance here must be W. Is there a way to express this using L and W? This is L and this is W. L minus W, thank you. This would definitely be L minus W. This right here. So then we could write that. We'll be looking at more word problems. Probably is slightly less difficult than this one, but this is good because if you can understand this, you should be able to understand the word problems we're going to get today for quadratics. Anyone have any questions about this that does not understand this? Because the fact is that when we cut out a square from a golden rectangle, we are given another golden rectangle, which means that the length of this golden rectangle to its width should be the same, should be proportionate to, or the same ratio as, the length of any other golden rectangle to its width. So doing this allows you to write this proportion using just L and W. Okay. If here, I want to know what the ratio is, couldn't I let W be 1? Wouldn't you agree that this guy on a calculator, it's like you could basically let W be 1 to figure out what L would be. Okay, so let's do that. So let's let W be 1. Let W equal 1. So if you did that, you can start there 1, 1, 1, 1. And this here is L, this is the L minus 1, as we're going to see here. So now we have everything in terms of L. So L over 1 is equal to 1 over L minus 1. I don't know why this TV is now humming this. Now, I think you said cross multiply. You guys see that? Whenever time you have a proportion or a ratio equal ratio, a fraction equal fraction, just go ahead and go into cross multiplication. So if we did that, we would have L times L minus 1 is equal to 1 times 1. Stand over here. So we continue this on the next page. What do we get here? How do we solve for this? Go ahead. Distribute, yeah. So L squared minus L is equal to 1. Continuing forward. We know it's a quadratic, right? And now here, is this prime or can we factor? If it's prime, we have to apply the quadratic formula to solve for L. And that looks like the scenario that we're in because I can't think of any factors of -1 that can sum to -1. All right, you'd be stuck at -1 plus 1, which is 0, which is not -1. So you have to go into the quadratic formula, which says that L would be equal to negative b. So we have -1 plus or minus the square root of b squared minus 4ac all over 2a. Just applying the quadratic formula. You guys need to have memorized. So continuing over here, -1, +1, plus or minus the square root of what this come out. Does anyone get this? This would come out to. What's that? Is this whole thing, this whole radicand 4? That's not what I got. Anyone else get anything different? No, it's 5. It is 5, so you got to be careful here. So we have -1 squared, which is +1, minus -4. So 1 minus -4 is 5, so be careful with that. All over 2. So if you just let W be 1, then by finding L, you found L over W, which is the golden ratio. Now, which of these, are both of these going to work, or is only one of them going to work? Yeah, if we did 1 plus √5 over 2, we'd have a positive divided by positive, which is positive. And then 1 minus √5 would be a negative value, because √5 is greater than 2, definitely greater than 1, so you have a negative value. So the only one that works is when we have the plus. So we only interested in the plus. So therefore, the golden ratio is exactly equal to 1 plus √5 over 2. So this is the exact value. This is the answer that we're looking for. Yes? You have to go. Okay. Raise your hand if you're lost with this problem. If you're not sure of it, not sure how we got to it. Yes? Where did it get started confusing? At the beginning? Okay. So what's neat about this this rectangle? What's neat about this rectangle is that the way it works is by you taking out a square, you just made a rectangle that has the same proportions as the rectangle you started with. That's what makes it a golden rectangle. So if we continue that process, if I cut out another square, then that rectangle that I made here would be another golden rectangle. to where its proportions are the same as this guy's, which is the same as this guy's. So when I say that two rectangles are proportionate, does that make sense? You sure? Okay. So that being said, if I let this be L and this be W, then this would definitely have to be L minus W. Right, this is W because this is square, so W, 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 W. L minus W would be this. This would also have to be W because this is a square. So we can express now the length of this golden rectangle that we developed here as W, and the width of it as L minus W. So if we're saying we're developing a rectangle that has the same proportions, then the length of the big rectangle to its width should equal the length of the smaller rectangle to its width. And by doing this and letting W be 1, because we want to know the ratio of L over W, so let's let W be 1. By solving for L, that you would find the golden ratio. This might also be a little thing that's a little, now I want to say it's a trick, but it's a little piece of information that you have to be intuitive enough to think about to do this in order so that you just have a single variable equation, which ends up being a quadratic. All right. So there's another number. So let's look at another problem from the text. Some more quadratic equation problems. We looked at 134 and 135 in the last class. 136 is just 135 continued. 137 is golden rectangles, which we just looked at that. I think Pythagorean's theorem and square root property is pretty straightforward. I'll just go to one real quickly. So 138. It says a rectangular park is 6 miles long and 3 miles wide. How long is a pedestrian route that runs diagonally across the park? So it's 6. It says 6 miles. Yep. And 3 miles wide.
What page you said this is on?
This is on page 154.
Oh. So there's a top of number 1.
Yep.
That's
Thank you.
why I was confused.
Thank you. So they want to know this.
Oh, glad you put that in
It is the Pythagorean theorem would be used to find this. Yep. Very good. This would be should be very simple. So how would I find? We'll find this distance. How do we find that? Okay. What would I write? Okay. That's the Pythagorean theorem. So let's just go ahead and go into it with these figures. 6 squared plus 3 squared equals d squared. Very good. Yep. This should be fundamental for you guys. Should be pretty solid. If we kept going, 6 squared plus 3 squared, 36 plus 9 is 45. I might be doing 36 plus 9, 45. So 45 equals d squared. So therefore, d would equal to the root 45.
Is this like, what is it called? Did you do this with, is this one? Like, someone, I guess it's as squared 2x.
I'm not sure.
You're talking about like trying to find a tangent?
Something like that. I think it's called in that. Calculate, and then it's like one side as 2x. I don't remember what it's called.
Okay, there is a 30-60 triangle
That one.
where you have a ratio of, say, the short side is 1s, the hypotenuse would be 2s, and the other leg would be square root 3s. Would that, okay, so let me ask you this, is this a 30-60 triangle? Oh no, you should. You brought it up, so I'm gonna ask you. Do we know, without these figures here, what type of right triangle this is? Even if we only had one? You would know specifically what kind of right triangle it is? You would? If you look at it? Okay, so we do know this is 3 and this is 6. So is this can anyone tell me if this is a 30, 60, 90 right triangle? You thought it was a 45, 45? What do you guys, can anyone help me out here? Can anyone help us out? What if we know the angles of this triangle? Just quickly off the top of our head, whether it's a 30, 60 or a 45, 45, one of those two common ones. Why is it not 45, 45?
All the sides are just.
Yeah, because these are not congruent. It's definitely not a 45, 45. Okay, so is it a 30, 60? You think it is?
Yeah.
We do have enough evidence to determine whether it's 30, 60 or not. So since it was brought up, let's go over that. Because this is good because you have to think about certain things. So what are the ratios? So you like to say S, okay? So we'll call this S. What are the other ratios for a 30, 60? Okay, of course, here's your right, here's your 60 degrees, here's your 30 degrees. What's 2S? The hypotenuse. The hypotenuse is 2S. Very good.
The other one
It is the square root of 3S. In case you forget, you can always use what theorem to find the third one. You can only remember two of them. Pythagorean theorem. So this squared plus this squared should equal this squared. Let's see. So S squared plus this squared, which would be what? 3S squared. Does that equal 4S squared? It does. So you know you completed it. So the question is, back to the original question, is this triangle here a 30, 60, 90 right triangle? Definitely. So let's say I take this triangle and I do this with it. The ratio should be the same. Meaning if this side is S, then this hypotenuse should be twice this distance, and this side length should be square root 3 times this distance. Is that the case?
No.
Right, it's not the case. So this is not a 30, 60, 90. It's obviously not a 40, 45, 45, 90. But it's a good thing to review this. It's not bad. Since it was brought up, let's be absolutely clear that this is not a 30, 60, 90 right triangle.
So it's just
It's
a triangle.
a right triangle. It's a right triangle. So the question in the book was how long is a pedestrian route that runs diagonally across the park? It says express answers in simplified radical form, then find a decimal approximation. Is this fully simplified? Okay, what is it? Do we know what it simplifies to? No, that's not. That's a rounded value. If I want to keep it in radical form. What's that? You say 5 square root 5?
Is it when you pull
This is a good review for you guys. It's advanced topics, simplifying radicals. See if something comes back, yes? So you say break this up and now you have 5? Does everyone agree with that?
Yeah.
Okay. Then what?
9 is 3. It becomes 3. Yeah, 3 comes out and then square root of 5.
Uh-huh. Very good. And then they also want decimal approximations. If someone with a calculator, what'd you get? Someone gave me a decimal. It's 6.7. So approximately 6.7. So this is just Pythagorean's theorem, which we should all know. Okay. On page 155. Oh, by the way, I think I've already mentioned to you guys, but I'll go over it again. I've only noticed a few have joined. Go ahead and join Blackboard so you have access to all these flip charts and all the videos that I'm recording, like this one right now. Page 155, number 150. It reads, a machine produces open boxes using square sheets of metal. Okay. The machine cuts equal-sized squares measuring 3 inches on a side from the corners and then shapes the metal into an open box by turning up the sides. If each box must have a volume of 75 cubic inches, find the length and width of the open box. Okay, so this is a problem that's essential to where you need to be able to look at a word problem and write a statement from it. You first have to be able to visualize something, so it doesn't hurt to always make a quick sketch of what they're talking about. So I'll read it again. A machine produces open boxes using square sheets of metal. So they have square sheets of metal. And what do? They say the machine cuts equal-sized squares measuring 3 inches on a side from the corners. So this thing ends up cutting and it says that 3 inches. I'm going to use the abbreviation. Then shapes the metal into an open box by turning up the sides. So now you have to imagine that you have a sheet of metal, and you have cutters that are strong enough to cut the metal. You cut out a square in a corner, cut out a square, cut out a square, cut out a square, and then you fold this up. So you have to really visualize this.
Oh, I see it.
So now you have to be able to see it. So once you see it, then it's like, okay, now I can go to the next step. But you have to be able to see it first. So this might be difficult for me to draw in 3 dimensions, but you just have to imagine, cut out these corners, fold it up, you would have an open box. Where now this here would be the base, right? So we've cut this out, so let's go ahead and show that.
Since it's a square, is it feel like the length in which we use measurements that well?
Good point. Good. So let's keep going here. So this is where you need to write things that maybe using a variable, some things you might not know. So you just said that this length and this length should have been the same. So if we end up cutting 6 inches on this side and 6 inches from this side, it should also be the same. Okay? So we agree that we'll call it, now what do you want to call it? If we fold these up, do you want to call this distance here L? Right?
It doesn't matter.
It really probably doesn't matter. But just in terms of think intuitively, we'll call this here L.
Yeah.
So all these are L. So we fold this up. What would you call the height? Or do we know the height?
That's 3 inches.
It is 3 inches, right? Because if I fold these up, the height is 3 inches of this box. So this is the H. We already know it. And the width, well, hold on, it was a square. We cut out 3 inches on each corner. Yeah, we got 9 square inches from each corner. So wouldn't the length and the width are the same thing? Okay. So, and they're talking about if each box must have a volume of 75 cubic inches, find the length and width of the open box. Okay, that's almost sounds like it might be a trick question to me. Find the length and width of the open box. They didn't say height, they said the length and the width, which are the same thing to us because it was a square. All right, so volume is equal to what? Yeah, so we know it's 75, so I'm going to substitute that for V. But what's the volume formula for? Yeah, good. Length times width times height. And in this particular problem, H is 3, and we all agree, everyone agrees that length and width are the same for this because the base is a square. So length is width for this problem. 75 is given. They say if each box must have a volume of 75 cubic inches, find the length and width of the open box. So if we find the length, we've also found the width. Well, let's complete this statement first. So length is, that's the one we don't know. The width is length, so I'm going to keep it in terms of L. So we have L times L, and we know the height is 3 inches, right? So we keep going here. 75 would equal to what? 3L squared. And you say divide both sides by 3 to get closer to solving for L. So if we divide both sides by 3, 25 equals L squared. And then L would equal to 5, right? We square root both sides. So yeah, so what would this be, this units for this length here? It would just be inches. And of course, the width is the same thing. It's also 5 inches. Anyone have any questions about this problem? I think the trick is to visualize it. Once you see it, okay, I can see the box now. Even though it's an open top, the volume formula is still consistent because the amount of space it occupies. It doesn't have to have a top. Now, its surface area would be different than, of course, it had a top and not having a top. That's not a concern for volume. So now I'm going to give you a couple homework problems to look at. Try on your own.
Not a full.